Hi everyone, my name is Joel Kamerka. I'm joined for this presentation by Ryan Lester, and we're representing our teammates Wyatt Gratz and Zeke Marshall as a group from the Material Science and Engineering Department, sponsored by EC Industries. Today we'd like to give you an overview of our project that worked to increase the modulus of cast aluminum for stiffness-limited applications.
Looking at trends over the past few years and projections for upcoming years, it's clear that the demands for fuel efficiency in the automotive industry are growing rapidly. On the left of the screen is a figure from 2019 that shows the trajectory of government-imposed standards on fuel economy. Even though administration changes have altered the scale of the efficiency goals, it's clear that manufacturers of these transportation products are needing to innovate and adapt.
Because of this need for better efficiency, many companies have used lightweighting as a main strategy to increase fuel economy. This equation shown models fuel consumption in passenger vehicles. The red arrows are pointing out two terms in the equation for vehicle mass, showing how much of an impact the total mass has on the resulting fuel usage. Understanding this, design engineers have focused on reducing part weight because it's a variable they can easily control with large-scale benefits.
Because of their low cost, wide range of strengths, and high availability, cast irons and steels are traditionally make up a large majority of automotive components seen on vehicles today. When looking at viable options for lightweighting, each has their own pros and cons. Titanium alloys have low density and high stiffness, but the cost is high compared to the other materials. Magnesium alloys, while low in density, have incredibly low stiffness, which is hard to overcome. With a low density, middle-of-the-road stiffness, and relatively low cost, cast aluminum alloys serve as one of the best solutions for the lightweighting of automotive components.
With aluminum selected, the new alloy will use elements that are common in the aluminum casting industry. A356 is an inexpensive and well-understood alloy, so the new design will add manganese and nickel in combination with A356, because these elements can increase the stiffness and be sourced ethically. Then, the target modulus gain from the alloying is to be around 10%, moving from roughly 70 to 80 gigapascals. Finally, the alloy needs to be cast fairly easily without needing large-scale changes to a conventional casting process. So now I've mentioned the stiffness increase we're looking for and this idea of remaining castable. But let's look more into where stiffness really comes from and how that sets up for castability. On the left, you can see a microscale image of aluminum alloyed with just nickel. And you can see areas that are darker and look smooth with lighter areas around them. These darker areas are called intermetallics, and they form in the casting process. These intermetallics are what help to make an alloy stiffer because they form shorter and stronger bonds that take more input energy to break. Now, knowing that, it might be logical to think to try and form as many intermetallic phases as possible, but there is a challenge to casting. Intermetallics cool, expand, and shrink at different rates than the material around them, so they can often form stress concentrations that lead to cracking and casting. Our design needs to find a balance between the stiffness gained from intermetallics and the complications to castings that come with them.
Exactly right, Joel. And these contour plots from testing and modeling are a great tool to find that balance. On the left side of the screen is a plot showing how modulus is affected by manganese and nickel that was generated from physical small-scale alloy trials. The plot on the right was generated through PanDat simulation software to show crack susceptibility. The highlighted region defines an area of high modulus and low crack likelihood, showing that a stiff and castable alloy is possible.
On the right is a general supplier to OEM sourcing structure for most manufacturing industries. If implementing this new alloy can let suppliers be more competitive by offering a better product, let manufacturers gain better fuel economy, and ultimately let consumer prices decrease, the opportunity for savings is very large. We believe that this alloy development is a good fit for use in several industries and could offer fairly immediate returns on investment.
Thank you so much